So we welcome Bastien Casier, which is now assistant professor in Université d'Artois. Yes. And unité de catalyse et de chimie du solide in Lille. So he was a former postdoc in the group of Dario, and he will present some work related to this activity. So
yeah. Thank you, Michael, for the nice presentation. So first, I would like to say thank you to the organizer to guest me today and allow me to present my research. So I will present my last postdoc, where I developed during this postdoc neural network to smartly classify in the full CI representation of the electronic wave function through an iterative machine learning classification. Okay, so now I just begin with a short introduction about what is machine learning, just to a pedagogical way. So machine learning is a part of the artificial intelligence where algorithms are designed to mimic the way of the brain to perform a particular task or function of interest. And historically, this algorithm can be analogical or simulated through a software. So behind this nice word, artificial intelligence, and the framework of machine learning, you have just statistics and linear algebra. And the most popular algorithm in machine learning can be, for example, neural network with deep neural network, convolutional neural network, or canal methods with canal width regression, decision tree, and so on. Okay, so why using machine learning in chemistry first? When we make quantum chemistry, ab initio quantum chemistry, we try to solve the Schrödinger equation here. That is really complex equation depending on a lot of parameters. And if you want to be accurate on this calculation, on the determination of the energy and the wave function, we need to apply a set of approximation. And when you try to reduce the degree of approximation, for example, if you start from Hartree-Fock and we want going to beyond Hartree-Fock, we need to include more and more accurate development of the wave function, but this effect have an influence on the complexity. Fortunately, during the 16th, with the emergence of DFT, density functional theory, we have the chance to obtain a good accuracy with a little complexity with n power 3. But it's not enough. We are again limited by the number of atoms, between 100 to 1,000 atoms in the system. So the computational costs stay quite high to describe very large systems. So the aim now is to use quantum machine learning, where the aim is to be accurate with a low computational cost. So the aim here is to describe particularly the chemical compound space, so the set of organic molecules, for example, on solids. And to do this, we need to apply a set of descriptors, like, for example, Coulomb matrix, smooth overlap of atomic position, molecular graph. And after, we need to train a particular algorithm that we choose, for example, neural network, canals, like I presented before, and we obtain a set of properties. So during this short presentation, I will just first introduce what is a full configuration interaction theory. And after, I will present the classification neural networks that I developed and that I call FCInet. And I will show you after application to polyelectronic systems and how we can after apply this neural network to define potential energy surface. Okay, so do the full configuration, the Schrödinger equation with the wave function, electronic wave function developed like a linear combination of different Slater determinants. And all these Slater determinants consist to build some excitation in the representation of the Hartree-Fock determinant. So you have the single excitation, double excitation, triple excitation that consists to promote an electron from occupied to a non-occupied orbital. And you have in the development different kind of stuff. So for example, the scatter determinants and the coefficient. And the aim here is to define, to obtain the value of the coefficients. And with the condition where the sum over all the square of this coefficient is equal to 1. To solve this full CI problem, we have two ways. The first way is a direct diagonalization of the full matrix or apply the variational principle. But we have a big problem, and this problem is a huge amount of determinants. Because, for example, for an open shell, it's a combination of n electrons in 2 multiplied by k, the number of spin orbitals, molecular spin orbitals. And in the closed shell, the problem is reduced, but stay really complicated. And the number of determinants increase exponentially. So to limit this number of, to select the most important determinants, so reduce the complexity of the development of the electronic wave function, we can use two approaches. First one can be a perturbative approach like SIPC that consists to determine the new coefficient to include in the variational space by a perturbation of the initial variational space that is constructed on a subspace of pre-selected determinants. So here I give you the equation for the first order, but you can develop this expression to the second order as well. Or the second way is to use directly the machine learning. So the aim here is to represent the determinant to some input vector, train a neural network or kernel, and obtain the coefficient like a combination of a parameter, so the number of ways involved in the machine learning model. Okay, so in the case of the classification neural network that I developed, I choose to use a binary representation of this determinant, and I based on the work of Jeremy Coe for regression of the coefficient, so where the representation is based on the. Give you a simple example with H2 in the basis 6311G, where you see that where the single excitation, where we promote the electron from the first spin orbital to the fourth spin orbital in the alpha block, so for the spin hub, for example, we can represent the determinant like this binary string, 0 and 1. After, we transform the outputs, so the coefficient, by two ways. We choose first a logarithm representation for the coefficient, or we use directly a classification, binary classification, where we define an important coefficient equal to 1 if the coefficient is upper than a particular threshold, or equal to 0 if this coefficient is under a particular threshold. After, when we applied this descriptor, this scaling transformation, so the conditioning of the data, we obtain a feature space, and in this feature space, we applied a minimization of the cost function. This is a learning, and the cost function that we used was mean square error or binary cross entropy. So during my work, and I will just resume some results that I obtained. We test, for example, logarithm representation and binary classification, but we observe that the logarithm classification doesn't work very well. So we choose to use binary classification, and for the cost function, we choose to apply the binary cross entropy to minimize the error. After, we choose to use this really simple architecture for the neural network, consisting of one hidden layer composed by n neurons, and we test different activation functions. For example, logistic activation function, hyperbolic tangent or the rectified linear unit function ReLU. After the datasets stay quite small in my case because we are under 1 million determinants. And so LBFGS method for the optimization for the learning stay correct to train the model. And finally, we test the quality of the prediction choose two quantities. The selection, that is represent the quality of the prediction. It's a ratio between the two important determinants and the number of real important determinants. And after the selectivity, that represents the quality of the selection, where we have the number of true important determinants predicted by the machine over the number of true important determinants and the number of false determinants. So after to do this, I applied a kind of iterative selection of the determinant. So we start with the data. The initial data normally is a CSD calculation. The determinant in the initial data is composed of each you have no combination between, for example, simple and countable. And the problem is doing CCPV-TZ, where we have close to 1,000 determinants. So it's just a toy system, but it's just to illustrate the influence of the training and the select. It's better. Ah, okay. And so I explained, yes, that I represent in this case, so the selection and the selectivity according to the training set size, so the like a percentage of the total Hilbert space, the total number of determinants. And in the case of H2, you have just single and double excitation, okay? Just S and D. And you can see, for example, that if we start with 20% of random chosen determinants, we have a quite poor selection and a quite poor selectivity. But when we increase the size of the training set, we obtain a better selection because we are close to 80% of a good selection of determinants. And the selectivity, so the errors that we do on the classification, weighs to 1, where the selectivity is perfect. I make no mistake in the classification. And this is due to the fact that we include, when we increase the number of training of determinants, we include more determinants, and for example, single and double determinants, that it's necessary to obtain a good, the good way where the determinants can be coupled together. So the connection between determinants. And so here I show you the influence of the quality of the classification according to the size, so the training set size. So for example, here we have just 20% of randomly chosen determinants, and you can see that the classification is not really good. So here you have in abscissa the number of determinants and the class of the different determinants. The red line represents the actual value, so that we need to attempt. And you can see that, for example, the machine classifies badly a large set of determinants in this case, because you have the machine predict, for example, a lot of important determinants that is not important in reality. And if we increase the number of training set size, for example, to 40%, you can see that the classification is better, because in this case, we make just 5 Wong classification of unimportant determinants. Okay, so in this case, the classification is better. So we have an influence on the training and on the convergence of the energy at the end. So for example, here I will show you with the blue sky line the value of the energy computed with the randomly selected determinants. So for example, with the 20% determinant, we have a high energy because due to the variational principle. And when we include more and more randomly determinants, you see that the energy decreases until the full CI reference. In fact, when we have at 100% of the full Hilbert space, we have the full CI calculation. And you can see that at the beginning, due to the Wong condition of the initial data, because we have not enough determinants and not enough determinants that couple together, we can see that it's difficult to reach directly to the full CI reference, because the machine have some difficulty to properly classify as the important determinant. But if we start from 40%, where the classification is good, and where the selection and the selectivity is good, we can reach to the full CI in one step, and we just in including less than 5% of the full Hilbert space. So the result here shows that the classification that we used allow to properly select the most important determinant, and with this protocol, we can hence reduce the size of the Hilbert space, and so the complexity of the Hilbert space and of the method to obtain the full CI reference. So now I show you an example with polyelectronic system. So I try the method with different kind of molecules. So for example, LEH, H2O, NH3, sorry, CO, N2, and C2H6, so the ethane. So I first try to apply the STO3G basis set, and we used for activated function in the hidden layer the function tangent hyperbolic, and we compare I compare my result with the CCSDT, that is the actual reference, the best computational method in proportion of accuracy and numerical complexity, with RBM, introduced by Giuseppe Carleo, and the full CI reference. And you can see that in the case of LEH, for example, we just include, we have 225 determinants, and we include just 53% of this full Hilbert space, and we reach directly the reference full CI, and we are better than RBM. Like in the case of H2 with 62%. And you can observe that when the system grows, the size of the Hilbert space decreases, and we reach to a proper solution less than, for example, the CCSD T reference, like in the case of C2H6, where we have 130,000 determinants. And in this case, we reach just by including 0.2% of this full size of determinant, we obtain an energy less than CCSDT. We apply the same calculation for other basis sets like CIS-3G with H2O and NH3, where the system presents 1,000 determinants, more than 1,000 determinants, or 9,000 determinants. And in this case, we just included 1% of determinants with a particular short cutoff for the coefficient, and we can see that in both cases we are under the value of the reference of CCSDT. So these results are really interesting for the next and for further application. So now I will show you a possible application of this approach that consists to build, for example, potential energy curves. So I show you, for example, the two potential energy curve for CO molecule and H2, and you can see that the energy, so the energy of the system according to the interatomic distance, is in perfect adequation with the full CI reference for each single point here obtained by full FCInet. So with the same protocols that I presented before for CO or for H2. And so the question here is, okay, I apply a classification, for example, for this point, for this point, for this point, and so on for each blue point. But my question now is, it is possible, for example, to learn simultaneously, all these blue points to obtain after a possible regression of this full potential energy curves. And so the question that I try to answer, and my idea, but I begin to implement this in my code, but I have some problem now, but I think that I can resolve the problem, is to, for example, define a different size of classical sphere, because each determinant are represented on a particular sphere. For example, if I represent the first sphere that I used in a simple system, for example, composed of 3 spin molecular system with 2 electrons, we have, for example, 3 vectors that represent the determinant represented on a particular classification sphere, and the machine learning, the neural network, find a way to separate the important and non-important determinant on this sphere. And so my idea is, okay, if I can do this on one sphere, maybe I can apply for this protocol for different sphere and learn simultaneously a neural network to obtain a full regression of the surface. And so, for example, the idea here is to multiply the initial vector that I showed you before with the example of H2 by the RMSD, for example, the root mean square deviation of the system. So in this case, in the case of diatomic molecule, just by the interatomic distances. And after the aim of this, for example, is if I obtain a good interpolation of the classification sphere, I can maybe opt to develop, for example, some particular interaction potential computed at the full CI level by applying this formula to obtain the interaction energy between system, and apply this, for example, for large system, like, for example, a drop of CO molecule, where the number of particles in this drop is quite huge. So to conclude this presentation, my aim was to present that the binary classification approach is a good way to smartly select the most important Slater determinants. After, the second point is that we have a very good convergence of the energy calculation according to the full CI reference, like I presented you before. And after, this method stay correct at the equilibrium position as well as at the dissociation limit, because we obtain a perfect dissociation curves, like I show you with molecule and H2. And finally, I hope, but I think it's in good way, possible interpolation to build, for example, potential energy surface, or at the beginning potential energy curves, to make a good interpolation by a simultaneous learning of different classification spheres. So I would like to acknowledge all the people that was around me, like, for example, my supervisor Dario Roca, and Basil Herzog, colleague and friend of me, and after Michael Badawi for his help, and Sebastian Ribeg as well. So thank you very much, and I'm ready for your question.
Thank you, Bastien.
Thank you.
Thank you. So, question. It was really.
Yeah, thank you for. Hi. Yeah. Okay, so thank you for your talk. I've got two questions. One on your curve of the discussion curve of CO.
Mm-hmm.
At I think it's at 3 on Shrum. You're above the full CI.
Yes.
Do you have an explanation?
In this case, I have a bad classification of the determinants, and okay, I can't reach to the full CI reference. And first, I have no really explanation of this problem because I observe this just at this point. But I present this just to be aware that yes, the method okay, doesn't work for each point. I prefer to be honest on my results. But for example, often we don't need to go to this dissociation limit, for example, because we can, for example, apply a cutoff at this point and consider after this radius that the energy reach a particular limit. Okay, because we obtain a asymptote, horizontal asymptote in this case. So it's not really a bad news for the development, for example, of interatomic potential. But currently, I'm not really, I don't understand exactly what's happened at this point. And I think
I already asked the question to Basil, but are you using also the selected Slater determinant at, let's say, at another point to feed your neural network at another point? Let's say you want to calculate at 3, you are using the selected determinant at 2.5.
Mm-hmm.
Are you using this trick?
So I'm not sure to understand. So, for example, you say
here you have at 2.1, you have, I don't know, let's say 1 million determinant or
right, yeah,
100,000 determinant. Are you using this selected determinant to the next point? Okay.
No. For each point, for each
you start from 0,
point,
from
I
scratch.
start to 0 and I make a selection. And it's for this reason that no, it's not enough to be really efficient at the next, because we would like have all the information along all the curve. And so it's for this reason that I try to apply, for example, spherical, different spherical representation to obtain different spherical, what can I say, classification sphere, and on it, I apply after a global neural network to make the regression over all this sphere, because I can just after multiply the initial representation of the determinant by a scalar value, a real scalar value, like for example the RMSD, because it's characteristic of the deformation of the molecule.
Okay, thanks. I've got another question, but maybe someone else.
Yes, by the way, simply if you do the training really in a very, so I have seen that you have done some training in STO3G. If you do the smallest basis set possible to do your training, you can still reach
smaller basis set than STO3G? Is it
well, smaller is going to be difficult.
No, yeah, it's quite difficult because it's already small. But I have just after the difficulties, the most difficulties of the problem here, it's when we increase the size of the basis set, the number of determinants increase a lot, and my representation here is based on screening of full determinants. So it's quite long to train the neural network on this case. But for example, we can maybe hybrid the two approaches with Basil and RBM, and this approach, for example, to generate the most important, classify if it's not, if it's good or not, or after applied, I don't know, my ID with the sphere, classification sphere for obtain the total interpolation between points.
Yeah, along the same line. So now I understand. You need to have the whole determinant to select them at different level of at each iteration.
Yes.
Okay.
So for example, if I can explain again. So for example, here I start with the CISD. Okay.
Yeah.
I make the representation. I apply the classification. Okay. Because I apply the diagonalization of the full CI matrix in CISD. Variational subspace, okay. After I classify the most important determinant predicted by the machine learning in the triple and quadruple excitation, and I include this in the data. And after I jump to the new space, okay.
Yeah,
but
I
apply the same process.
At the beginning, you are not in the full CI.
No.
So
okay,
so
I'm not in the full CI at the beginning. No.
So
I start at the CISD.
Okay, so now I understand.
Application.
So my question is, do you have a limit in terms of number of determinants or configuration that you can deal with? I mean,
yes.
With respect to the real full CI. I mean, when you add all the excitation, do you have some kind of limit or?
Yeah. We are limited by the size of the basis set, because the basis set defines the number of total determinants by this combination that I present at the beginning here. Yeah. So you have this total number of determinants, for example, for closed shell, like I discussed in the talk, and all these determinants are classified by single, double, triple determinants. And during the procedure, I begin with this determinants, and I predict the triple and the quadruple. And after, when I include this, I remove the non-important single and double determinants. So I reduce the size of my training, and I start with the triple and the quadruple to predict after the quintuple, hextuple, until I screen all the determinants. So, for example, in the case, for example, of H2 in the base of 6.G, I screen 1 million determinants. Okay, I screen 1,656,000 determinants. Okay.
Okay. So if the full number of determinants is too large, let's say over than 1 billion. It's
a problem. Yes, it's a problem of the approach. Yeah, because it's deterministic approach, not stochastic.
Can you stop before that?
We can. Yes. For example, if for example the energy reach to a particular limit, and if we see if you see that the energy begin to converge and doesn't change because the contribution of each determinant that we include have a very small contribution, we can stop this. In fact, we can stop at this moment. It's not really, but in this case, it's not really important because, for example, it's better to use a limit that is proportional to the size of the Hilbert space. Because, for example, if you have, for example, 10 minus 6 coefficient that is less than 10 minus 6, you know that in this case, this influence, for example, at 10 minus 9, never contributes to the full energy. It's just a very small contribution. But for example, you can see in the case where we use just 10 minus 4, the energy is smaller than CCS dt, but you see that we have again some determinants that contribute. And for example, we see that the value that we use for the threshold depend of the size of the Hilbert space. So for example, if you have 1 million determinants, you can apply a threshold close to 10 minus 6. And for example, if you have 1 billion, you will apply 10 minus 9. Okay, it's proportional to the size of the Hilbert space. Thank you. Thank you very much.